There we go. Okay. So graphing tangent and cotangent is the way that we do it is going to be very similar to the way that we graph sine and cosine and whatnot. The graphs themselves, though, will look pretty different. So let's see. So getting started here, this is going to be 4.5, graphing tangent and cotangent. Okay, so kind of on our way into this with graphing tangent, we're going to have, I guess, a similar equation starter, a similar general form to what we had with sine and cosine. So first of all, looking at f of x equals a tangent bx plus c plus d. So it's a very similar general form. A couple of things that are different, though. As you'll see in a moment, tangent doesn't really have amplitude. It is a cyclical function, but it's got asymptotes, and so it doesn't have like a maximum and a minimum value on tangent. So instead, we're going to have A be the vertical stretch. Or compression. So that's how we'll refer to A instead. B is still affecting the period. So changes period. You can also kind of think of that as horizontal stretch and compression, as we kind of talked about yesterday. And then C is that horizontal or phase shift. And then D is the vertical shift. And as you'll see, this horizontal or phase shift here is going to shift your starting point. Or it kind of shifts that center point of it. So in a very similar way to how if you're dealing with a parabola, something like that would shift the vertex. It's going to shift this point of inflection of our tangent function left to right, just as the vertical shift is going to shift that point of inflection up and down. So there's still some similarities also to actually calculating the phase shift and stuff like that. It's still calculated. Phase shift is still negative c over b. The period, though, the way we calculate the period change is different. Instead of 2 pi over b, it is pi over b. And that's because the standard period for tangent is pi. For tangent and for cotangent. Whereas for sine and cosine, it's 2 pi. So there is that difference there. And then the vertical shift is still D, and the vertical stretch and compression is still A. But again, it's not called amplitude when we're talking when we're talking tangent and cotangent. Okay. So I'm going to draw a graph of what the standard tangent curve looks like, and then we're going to jump over to the graphing calculator and kind of look at things from there and compare a bunch of tangent and cotangent functions. Okay. I'm going to scale the x-axis by every pi over 2. And the interesting thing with tangent and cotangent is that there's asymptotes. So one of the things that we will care about with tangent and cotangent is kind of a general equation for how we can find the asymptotes. So regular f of x equals tangent of x is going to have asymptotes that look like that. It's going to have a starting point here that's kind of this point of inflection. And we can see here that the period then is pi because every time it starts over, or every time it has an asymptote, the distance between the asymptotes is pi, because that's our generic period for tangent. So that's a couple of cycles of tangent. Okay, so for this one, if we were asked about vertical stretching and compressing, or I guess we can label a couple of the things that we would be asked for typically. So that A value is 1, vertical shift is 0, phase shift is 0, the standard period is pi. But then we want also that equation of the asymptotes. And that tends to be the part about tangent that people find the hardest, figuring out what is the equation of the asymptotes here. So we know the asymptotes are on things like pi over 2, negative pi over 2, 3 pi over 2, and so on. We're adding a pi each time, right? So we can say for the equations of the asymptotes, it's going to be x equals, because they're vertical lines for these asymptotes, pi over 2 plus n pi. Because each time that we add pi to it, we get another asymptote, right? And then n is just a generic index. So it's basically any integer that you want to plug in is a value of n. So I can plug in n equals 0, 1, 2, 3, 4, and each time I do, I'm getting another asymptote for this function. And we'll talk a little bit more about how we would find equations of asymptotes once we shift things around and stuff like that. But in the meantime, a lot of times you'll be asked for either the equation of asymptotes or for just a couple of examples of where asymptotes are located for that function. All right, so that's kind of the basics of tangent. Now let's go ahead and take a look at on a graphing calculator on Desmos, what it's going to look like and what some different shifting of that can do, or what changing values of A, B, C, and D will do to the tangent function. Okay, so let's go to Desmos. All right, and when you get to Desmos, the first thing I would do again is click the wrench. And I'm just going to go from negative 2 pi to positive 2 pi on the x-axis just to give myself a decent window. And then I'm going to have my steps be pi over 2. This is kind of a basic starting point. Then we're going to go ahead and take a look at tangent of x. Okay. So there it is. You can kind of see where the asymptotes will be, especially if you zoom out a bit. The asymptotes become a little bit more clear. But anyway, so that's what it would look like for kind of your starting point of just regular tangent of x. So then if we also wanted to have something like, oh yeah, I'm going to turn on projector mode so the lines are a little thicker. Tangent of x plus 2. So it takes this point of inflection, this center point here, and moves it up 2 for all of these. It doesn't change any of the asymptotes. It doesn't change the period, nothing like that. It just moves the thing up, as we would kind of expect. Okay, well, what if we did tangent of x plus 2? Well, that just takes our original thing and moves it to the left. Or what if I did plus, I don't know, pi over 2? So it takes the thing and shifts it to the left pi over 2. Or if we did tangent of 2x. Well, now there's more of them. So that changed the period. That makes it repeat more often. And that's what changes the asymptotes too. It moves the asymptotes around. Using phase shift like this can also change the asymptotes. Phase shift and the period change are what kind of changes where the asymptotes are located. And then lastly, or not lastly, let's do a couple of others. What if we did tangent of 1/2 x, or x over 2? So that creates less of them because it expands the period. So kind of like we saw yesterday with sine and cosine on the matching activity, when that b value was between 0 and 1, it made the period longer, and when that b value was greater than 1, it made the period shorter, increased the frequency. Or if we do something like 2 tangent of x. We can see that that's what our vertical stretching and compressing does. This is vertically stretched a little bit. It makes it kind of skinnier, but it doesn't actually change the period. It doesn't change where the asymptotes are located or anything like that. It just changes kind of the shape of it at the very beginning of each cycle. Okay, so there's a bunch of variations of tangent. What if we look at a variation of like cotangent instead? You can kind of see what cotangent does, which hopefully kind of makes sense, because if you remember what cotangent is, it's what you get when you flip tangent over, right? So this kind of reflects tangent. And it shifts it, so I mean, the starting points, it's still got the same period, the standard period of pi, but it's going in the other direction this time. And those points of inflection, our standard location is at every pi over 2 plus pi. Anyway, as far as graphing goes, you're not going to do a whole lot of graphing of these by hand. You don't do a lot of graphing of anything by hand anymore, but that's kind of how they work and are generally affected by changes to period and phase shift and vertical shift and all that good stuff. Okay. Any questions at this moment before we kind of move into talking a little bit more about equations of asymptotes? Okay. Then see if I can find what I was going to use. Okay. So let's focus on this one, for example. Oops, not that. Okay. So tangent of x plus pi over 2. So we can see that this one has just taken our regular tangent function that starts off with our point of inflection being at 0 and moves it over. So instead of having asymptotes at kind of like we saw here with the standard tangent function, the asymptotes are no longer at pi over 2 plus n pi, but instead we've got an asymptote at 0, at pi, at 2 pi, 3 pi. Those are all of our asymptotes this time. So instead, our equation of our asymptotes or sorry, not y equals x equals, goodness. We'd have pi or x equals 2 pi and 3 pi and 4 pi and so on. See if it'll do it with, nope, it won't. Bummer. Is there a way for it to be? No. Okay. Anyway. And so if you have kind of a hunch about where the asymptotes are going to be, you can plug in a few of them and see kind of where they end up. You can also take kind of your period and your phase shift to work out the asymptotes. So like for this one, we know that our period is pi, and we know that it's been phase shifted over pi over 2. So if our original equation of the asymptotes for a regular tangent function is pi over 2 plus n pi, this is what tells me, or this is what comes from the period right here. So if the period hasn't changed, you can leave it as n pi. The phase shift is what you have to work with then if it's been phase shifted, like this one has. So make this smaller so I can, okay. So since this one, tangent of x plus pi over 2 has been phase shifted over pi over 2, you can add or subtract a pi over 2 to this, and then it will get you the equation of asymptotes that will work with this one. So this part is what comes from the phase shift. This part is what comes from the period. Particularly this. So if your period, whatever your period is, goes there. Whatever your phase shift is, gets added or subtracted from that. So in this case, our if we were using this function x plus pi over 2, or tangent of that, then your equation of asymptotes would just be x equals n pi, or you could do n pi plus pi, because that would be the same thing. Okay. So that's pretty much everything we need right now about graphing tangent and cotangent. And finding tangent and cotangent from given characteristics. So we're going to do a couple of examples involving kind of like we did with sine and cosine, where I'm going to give us some features and we're going to take those features and put them into a tangent or cotangent curve. And then we're also going to do a couple where we're just given a tangent or cotangent curve and we're asked to find different features of it. So, because the graphing in and of itself that we've kind of talked about can be pretty easily done with a calculator. So we want to focus a little bit more on the other aspects. We want a tangent function with, let's see, a period of 2 pi, phase shift of, we'll go with 3, vertical shift of -7. Okay, so just like we did with the sine and cosine functions, we're working off of that a tangent of bx plus c plus d. So once we find a, b, c, and d, we can plug those in and we're good to go. On this one, it makes no mention of a vertical stretch or vertical compression or anything like that. So we really don't have to worry about a. A is just going to be 1. So if we don't have any vertical stretching or compressing mentioned, a is 1. For the period, though, we know that the period is going to be 2 pi. But for tangent, we got to remember that it's going to be pi over b, not 2 pi over b like it is for sine and cosine. So instead, multiply by b on both sides, we get 2 pi b equals pi. So b is 1/2. And then for the phase shift, we know that we want it to be 3, and that's -c over b. So then 3 is -c over 1/2. Multiplying by 1/2 on both sides, we get 3 over 2 is -c. So -3 over 2 is c. And then for d, we know the vertical shift is -7, so d is -7. So putting it all together into our final answer, f of x equals tangent of 1/2 x minus 3 over 2 minus 7. Okay. I'm gonna have you guys try one of these. So this time, we want a cotangent function with a period of 3, phase shift, let's see. We'll go with a phase shift of 2, vertical shift of 5. So go ahead and give this one a try. When you think you've got it, type "got it" in the chat. If you started off with A is 1 and D is 5, you're on the right track. And then to figure out B, if you started off with the equation pi over B equals 3, you're on the right track. All right, if you got pi over 3 for B, you're heading in the right direction. And then you want to set up the equation 2 equals negative C over pi over 3, since the phase shift is negative C over B. So then we should get that C is negative 2 pi over 3. So putting it all together, what do we get? Actually, that might be a bit of an annoying one to type. So we'll just put it together. F of x equals cotangent of pi over 3x minus 2 pi over 3 plus 5. Okay, so that's kind of one direction that these problems can take. The other direction that these problems can go is we can be given a function like this and asked what is the vertical shift, what is the period, what is the vertical stretch, things like that. What's the phase shift? So that's what we're going to do next, and that should cover all of the kinds of problems that we need. So the first one, we're going to have f of x equals 1/4 tangent of 2 pi x minus 4 plus 6. We want to know all those things: vertical stretch, phase shift, period, vertical shift for this function. So the first thing I would pull out is that vertical stretch and the vertical shift. Those are the easiest to identify right off the bat. So here's our vertical stretch. Actually, this one's vertical compression, but anyway, 1/4. Vertical shift. Of 6. Then moving on to the period, it's easier to sometimes if you can just identify first A, B, C, and D, because for the period, we know it's pi over B, which in this case is pi over 2 pi, which is just 1/2. Since the pi's cancel. And then lastly, we want that phase shift. So C is -4, phase shift is -C over B, so -4 would be +4. B is 2 pi. So in this case, the phase shift is 2 over pi if we reduce that. Okay. Any questions with this one? Any numbers we're not sure where they came from? Any steps we're not sure how they happen or why they happen? Yes, the negative on 4 is because C is negative. So this would technically be -4, which turns into a +4. Yeah, good catch though. We do want to be careful with that. Yeah, if anything out here has a sign attached to it, you want to make sure you keep that with it, except for B, because technically it's over absolute value of B. So whatever you have, if like you have a negative value for B, change that to a positive. Okay, let's do another one. Let's go -3 cotangent of 4x minus 9 minus 14. All right, so for this one, let's help me out here. What's the vertical stretch going to be? Right, we've got a vertical stretch. And actually, I'm going to say it's a vertical stretch of 3, but the negative does tell us something. It tells us it's been flipped. So just kind of like with, let's take a look at what that looks like graph-wise. And you can always also, just to make sure that you've got all of these things labeled correctly, you can always type this function into a graph and to double check that it is what you think it is. Well, let's take a look real quick at what happens if we have tangent of x versus negative tangent of x. So it reflects it, right? Dancing. Anyway, yeah, so it reflects it over the x-axis there, or y-axis. Actually, it would look the same either way. It's reflected over x or over y. Anyway, interesting things to think about. But I guess since it's outside with the y, it's reflected over the y-axis. So this one, we could say it's vertically stretched and it's also reflected. All right, what else? What's the vertical shift? What's my vertical shift going to be? Yeah, negative 14. What about the period? Period might take a little bit more work. You have to do the whole pi over b thing. What do we get? Yeah, we can just leave that as pi over 4 because b is 4. So pi over 4 would be the most exact form of the answer of the period. Anytime there's a pi involved, as long as you reduce all other fractions that are going on, you're good to just leave the pi in there, especially if you're asked for something as an exact value. Obviously, if you're asked to round something to the nearest tenth or the nearest hundredth or whatever, then you want to make sure that you multiply by pi or whatever it is that the pi is doing in there. But in this case, most of the time, you're just going to want to leave the pi as pi. All right, last one, the phase shift. Negative c over b. What do we get? Yeah, exactly, 9/4. Because c is negative 9, so it's negative 9. B is 4. So that just becomes positive 9/4. And I would just leave it as positive 9/4 as well. If you really, really want to, you can put it as 2.25 since that's still an exact value since it's a terminating decimal. But why do the extra work? Just leave it as 9/4. Okay. So that's pretty much everything that we need on a scale of 1 to 5, 1 being I'm completely lost, 5 being this is super easy. Let me go work on stuff on my own. What are we feeling? Okay. Seeing a pretty big mix. Yeah, some people just was like, I need to do some problems. I need to do some on my own. Okay. So here's what we'll do. I'm going to post the assignment. And then if you would like to stick around and do more problems with me or get help on some problems, please stick around. Otherwise, I'm going to let you go and work on things on your own. So I'm going to post the homework here.